James Webb caught a chemical fingerprint in a distant planet's air that no model predicted. On the exoplanet K218b, 124 light-years away, researchers reported a possible trace of dimethyl sulfide in April 2023 and again in April 2025. On Earth, that molecule is made almost entirely by living organisms, but the signal flickered near the edge of what the instruments can even detect. So was this the discovery of a century, or a ghost inside the data? That question hangs on one strange molecule. Dimethyl sulfide, or DMS, has a specific origin story on our world. It comes almost entirely from marine phytoplankton, the drifting microscopic life that fills the oceans. When those organisms live and die in vast numbers, they release DMS into the air. Earth's oceans pump out an estimated 28 million tons of the compound each year, and it rises so reliably that atmospheric chemists trace it as a marker of ocean productivity. A single species, the Coccolithophore Aemiliana huxleyi, blooms across thousands of square kilometers of the North Atlantic every spring and floods the sky above it with sulfur. So finding it elsewhere is like finding a footprint on a beach you thought was empty. The beach here is K218b, and it is nothing like Earth. It orbits a cool red dwarf star in the constellation Leo. The star, K218, is a red dwarf roughly 40% the mass of our Sun, and the planet circles it every 33 days at a distance so tight it would sit well inside Mercury's orbit. The world was first spotted in 2015 by NASA's Kepler spacecraft during its extended K2 mission, which is where the name comes from. The planet weighs around 8.6 times the mass of Earth, too big to be rocky, too small to be a gas giant like Neptune. It measures about 2.6 times Earth's radius, and it sits in that awkward middle category, and some scientists called it a possible Hycean world, a planet wrapped in hydrogen with a warm ocean underneath. An ocean, a hydrogen sky, and a molecule tied to life. That combination is why the confrontation matters. No standard atmospheric chemistry predicts DMS floating in a hydrogen-rich alien atmosphere, and yet the light coming back from that planet seemed to whisper its name. To understand why that whisper is so hard to trust, you first have to understand how Webb listens at all. Because here is the strange truth. Webb never actually sees this planet. It cannot photograph K218b as a disk. The world is a speck lost in the glare of its star, which outshines the planet by a factor of thousands even in the infrared. Instead, Webb uses a trick of timing and light called transit spectroscopy, turning starlight itself into the messenger. As the planet crosses in front of its star, a thin sliver of starlight passes through the planet's atmosphere on its way to us. That air acts like a filter. The transit itself lasts only a few hours, and the atmospheric signal it imprints changes the star's brightness by mere tens of parts per million, a shift smaller than 1 part in 10,000. Different molecules absorb specific wavelengths of infrared light, each leaving its own dark notch in the spectrum. So the light that reaches Webb carries a shadow record of everything it touched. Turning that faint shadow into chemistry is the job of Webb's instruments. NIRISS, NIRSPEC, and MIRI each split the incoming light into a spectrum, spreading it out like a rainbow so scientists can read the gaps. NIRISS covers wavelengths from about 0.6 to 2.8 microns. NIRSPEC extends further into the near-infrared, and MIRI reaches all the way out to 28 microns. The first K218b results leaned on 2 transits observed with NIRISS and NIRSPEC, each one a precious slot of telescope time on the most oversubscribed observatory in history. Every dip is a fingerprint. Match it to a known molecule, and you have named a piece of an atmosphere you will never touch. That is how Webb gave K218b its first real identity. And that identity was genuinely exciting. In 2023, JWST data revealed clear signs of methane and carbon dioxide in the planet's atmosphere. These were confident detections, fitting cleanly into the spectrum. For the first time, an atmosphere on a world this size and this far away had a chemical portrait. What was missing told an even richer story. The data showed no strong sign of ammonia, and that absence was a clue. In a deep hydrogen atmosphere, ammonia should build up unless something removes it. A vast ocean of water could soak it away. So the missing ammonia hinted at a hidden sea beneath the clouds, exactly what a Hycean world would have. This work was led by Niku Madhusudhan and his team at the University of Cambridge, and it drew immediate attention. The findings appeared in the Astrophysical Journal letters in September 2023, and NASA amplified them in a public release the same month. Madhusudhan had coined the term Hycean only in 2021, blending hydrogen and ocean, and K218b became the first real test case for the idea he had proposed. A sub-Neptune with methane, carbon dioxide, and a possible ocean was already a landmark. But buried in the same spectrum was a fourth possible molecule that refused to sit quietly in the background. That fourth signal was the faint suggestion of dimethyl sulfide. It was not a bold line, but a weak feature, a soft dip in the light that seemed to match DMS, but only barely. And the moment the team saw it, they also saw the problem. The signal was not strong enough to trust. In the language of physics, that first DMS signal sat below 3 sigma confidence. Sigma is a measure of how unlikely a result is to be random noise. 3 sigma already means the odds of a fluke are small, but this was even weaker. And in the world of discovery, weak is not enough. The gold standard is far more demanding. To claim a genuine detection, scientists want 5 sigma confidence, a threshold where the chance of an accident becomes vanishingly small, roughly 1 in 3.5 million. It was the same 5 sigma bar that physicists at CERN insisted upon before announcing the Higgs boson in July 2012. A signal below 3 sigma is not a discovery. It is a lead, a reason to look again. So the team did the right thing. Before celebrating, they turned to hunt for the ways they might be fooling themselves. The first suspect was the instrument itself. Webb is a machine of extraordinary sensitivity, but sensitivity cuts both ways. Its detectors show correlated noise, small errors that ripple across neighboring wavelengths in patterns. Those patterns can, by pure chance, mimic the gentle curve of a molecular fingerprint. That makes data reduction a minefield. The raw signal from Webb is not a clean spectrum. It has to be processed, cleaned, and calibrated through a long chain of software choices. And here is the uncomfortable part. Faint features can appear or vanish depending on which choices you make. A tiny decision in the pipeline can conjure a ghost, so researchers fight back with repetition. They run the same observations through multiple independent pipelines, each built with different assumptions. If a signal is real, it should survive no matter which road you take. If it only shows up under one specific recipe, that is a warning. The DMS feature was fragile enough to demand exactly this scrutiny. But noise was not the only rival explanation. Even if the signal was real, it might not be DMS. The wavelengths where dimethyl sulfide absorbs light are crowded. They overlap with methane and other hydrocarbons that could easily live in the same atmosphere. 2 very different molecules can leave marks in nearly the same place. This opened the door for other teams to test the claim. The JWST data was made public, and independent researchers pulled it apart on their own terms. Within weeks of the 2023 announcement, groups including a team led by Nicolay Lewis at Cornell and another headed by Raphael Luque at the University of Chicago downloaded the same public files and ran their own reductions. This is science working as it should, with no single group owning the truth. And what several of these reanalyses found was sobering. They did not see the same story. Several independent teams reported no statistically significant DMS at all. Where the original analysis saw a hint of life's fingerprint, others saw only overlapping methane and ordinary chemistry. The signal, in their hands, dissolved. The deadlock could not be broken by arguing over the same spectrum. To move forward, the team needed new eyes, not new arguments. So in April 2025, they came back with a different instrument and a different slice of light. This time they used Webb's MIRI, its mid-infrared instrument, aimed at a wavelength range the earlier observations had not covered. The choice of MIRI was deliberate. The mid-infrared is a region where DMS and its chemical cousin dimethyl disulfide, or DMDS, both absorb strongly in the band between roughly 6 and 12 microns. The new campaign captured a single transit with MIRI's low-resolution spectrometer, adding fresh coverage the 2023 datasets had never touched. If those molecules were present, this was a place they should announce themselves clearly. And crucially, this observation was completely independent of the earlier NIRSpec and NIRISS data. That independence was the whole point. A second, separate detection in a different wavelength range would be far harder to dismiss as a pipeline artifact or a fluke of one instrument. If DMS showed up here too, in fresh data, the case would grow real teeth. And when the results came back, the signal did look stronger than before. But stronger is not the same as proven. The reported significance of the 2025 result came in at around 3 sigma. Better than 2023, but still parked right at the edge of respectability. The detection favored DMS, or DMDS, or some mixture of the two, without cleanly separating them. 3 sigma sounds impressive until you sit with what it means. It corresponds to roughly a 0.3% chance that the signal is random. That may sound tiny, but in the hunt for life beyond Earth, tiny is not enough. Scientists have been burned before by results that looked solid at 3 sigma and then evaporated. The 2020 claim of phosphine in the clouds of Venus is the cautionary tale everyone cites, a headline biosignature that shrank dramatically once other teams reprocessed the data. The bar has to be higher, precisely because the stakes are so high. And even if the molecule is real, a deeper question waits underneath. Can non-living chemistry make dimethyl sulfide without any biology at all? Because DMS only means something as a sign of life if life is the only thing that can make it. The answer is unsettling. DMS has been detected on Comet 67P by the Rosetta mission, a frozen, lifeless chunk of ice and dust drifting through space. Rosetta's ROSINA instrument sampled the gas streaming off Comet 67P/Churyumov-Gerasimenko during the spacecraft's rendezvous between 2014 and 2016, and a 2024 reanalysis of that archive flagged the DMS signature. There was no ocean, no phytoplankton, no biology of any kind, and still, the molecule was present. Both laboratory experiments and that cometary evidence now show that a biotic DMS is possible. Non-living processes can build this molecule under the right conditions. That single fact undercuts the whole dream. It means DMS is not a clean biosignature. Finding it does not automatically point to living things because the universe has other ways to make it, and the doubts do not stop at the chemistry. Critics argue that the very nature of K218b is still unsettled. The hopeful picture of a warm ocean under a hydrogen sky is only one interpretation of the data. It is a beautiful story, but not the only one that fits. Some models paint a far harsher world. Instead of a gentle water ocean, they suggest a magma ocean, a surface of molten rock beneath a scorching atmosphere. A hot, gaseous interior would rule out habitability entirely. There would be no cool sea for phytoplankton, just heat and pressure. So the High-Sean interpretation remains contested. Take away the ocean and the whole narrative shifts. The DMS signal, even if real, would then be floating in an atmosphere with no plausible biology beneath it. This is why the community refuses to leap. Too many pieces of the story are still unproven. Faced with all this, science does what it always does under pressure. It sets the bar and refuses to lower it. Extraordinary claims demand repeatable, independent data, and the claim of life on another world is about as extraordinary as they come. Enthusiasm is not evidence. The requirements are clear. A true discovery needs 5 sigma confidence and independent confirmation from separate observations and separate teams. The DMS signal has met neither. It sits at 3 sigma, and the reanalyses still disagree. That is not failure. That is the system protecting itself from wishful thinking. So the work continues. More JWST transit observations of K218b are planned, gathering more light, more spectra, more chances for the signal to prove itself or fade away. Madhusudan's team has estimated that around 16 to 24 additional hours of MIRI observation could push the result toward the 5 sigma threshold, and further transits have been requested in Webb's oversubscribed observing cycles. And peer reanalysis keeps stress testing the DMS claim. The molecule will either survive this gauntlet or it will not. Yet even if DMS vanishes tomorrow, something remarkable already survives. Set aside the question of aliens, and a genuine breakthrough remains. Webb characterized the atmosphere of a sub-Neptune, a world type utterly absent from our solar system, in this much detail for the very first time. That alone was thought to be extraordinarily difficult. The confirmed findings carry real weight. Carbon-bearing molecules like methane and carbon dioxide reveal that this atmosphere is chemically active, alive with reactions we can now begin to trace. This is a world with a working sky, and we read it from 124 light-years away. That is not a footnote. That is a milestone. Because of it, K218b has become a benchmark, a reference point for exoplanet habitability studies, the world against which future observations are measured and future methods are tested. Whatever the truth about DMS, this planet has already taught us how to interrogate an alien atmosphere. It changed the questions we know how to ask, and that reshaped something subtle but important. The story of K218b redraws the line between a hint and a discovery. It shows, in public and in real time, how much space sits between a flicker in the data and a claim you can stand behind. That gap is where honest science actually lives. So let the record be plain. No confirmed detection of life has been announced, not on K218b, not anywhere. What remains is the DMS signal itself, a tantalizing anomaly that will not fully confirm and will not fully die. It is exactly the kind of puzzle Webb was built to chase, an observatory launched on December 25, 2021, to enable precisely this work. ATTHE-EDGE-OF detection. That is where this discovery lives, and there is no shame in it. K218b has given us a working atmosphere, a genuine method, and a mystery worthy of the years of scrutiny still to come. The signal is not proof of life, but it is proof of how far we can now reach. If this story of light, doubt, and distant worlds moved you, consider subscribing to follow where the next transit leads.